Hi, Assalamualaikum. Welcome back to my channel, Physics from 5 KSSM. Today we start Chapter 4, Electromagnetism on topic 4.1, Force on Current Carrying Conductor in a Magnetic Field. I will discuss three learning standards. The first one describe the effect of current carrying conductor in a magnetic field. The second one, draw the pattern of combined magnetic field to indicate direction of force on current carrying conductor in a magnetic field. And the third one, explain factors that affect magnitude of force on a current carrying conductor in a magnetic field. If you look at the picture here, these are examples of electrical appliances that using motor. As we know that the function of most electric motors is based on the effect of current carrying conductor in magnetic field. The function of motor in electrical appliances is to convert electrical energy to mechanical energy. As for example, the stand fan here, the function of motor able to rotate the blade of the fan. Or the vacuum cleaner, the fan inside the vacuum cleaner requires motor to rotate it. Let's look at activity 4.1. The aim of this activity is to study the effect on current carrying conductor in a magnetic field. Apparatus required: low voltage DC power supply, U-shaped steel yoke, a pair of magnet and retort stand. Materials: 2 copper rods without insulation and copper wire also without insulation, or we call it bare copper wire. Okay, what happens to the wire when switch is on? Okay, watch this video. What happens to the wire which is initially at rest? Switch is on. You can observe that the copper wire move. The basic principle in physics, when an object which is at rest moves, means there is force act on the wire. Where does the force come from? Can you explain how the force that moves the wire is produced? Let's discuss further on this topic. Look at this one. This is also the same situation, but now the wire is connected to the connecting wire and hang it so that it will swing. Observe what happens to the wire when the switch is on and when the terminal of the battery is reversed. When the switch is on, so you can see the wire displays to the left. When the switch is off, return to original position. Now reverse the terminal. So you can see the wire now swing to the opposite direction or move to the opposite direction. Can you explain this situation? Let's discuss some questions involving the activity carried out. Number 1. Describe the motion of copper wire when the power supply is turned on. As you can see in the video just now, the copper wire carrying current in magnetic field experiences a force and moves. What is the effect on the copper wire when direction of current is reversed? The pole of magnet are reversed. We observed just now, when the direction of current reversed, meaning the terminal is reversed, the copper wire moves in reverse direction. This is because direction of force act on the wire is also reversed. The same thing happens when the poles of magnet are reversed. Direction of force is also reversed by reversing polarity of the magnet. So from here we can state two factors that affect direction of force acting on current carrying conductor. The first one is direction of current. The second one is polarity of magnet or direction of magnetic field. What caused the force act on the wire? When a current carrying conductor plays a magnetic field, you will observe that there is a force act on the conductor. Can you explain how the force is produced? You have studied before, when the current flowing through a conductor, there will be magnetic field around the conductor, especially when we discuss about straight wire. There is magnetic field around the wire, concentric circle shape. When we place the current carrying conductor in magnetic field of magnet, the magnet also has its own magnetic field. Thus, there will be interaction between the two magnetic fields. The interaction between the two magnetic fields will produce resultant magnetic field, or we call it catapult field. This non-uniform field will produce net force that acts on the conductor. The force that produced, we call it force on current carrying conductor in a magnetic field. This is how the force produced when you place a current carrying conductor in the magnetic field of permanent magnet. Now we want to try to sketch the pattern for the resultant magnetic field or catapult field. And then direction of force that act on the current carrying conductor also can be determined by using Fleming's left-hand rule. What is this Fleming left-hand rule? Let's look at how it works. So this one is a wire that plays a magnetic field of permanent magnet. We can use Fleming's left-hand rule to determine direction of force that act on the wire. The thumb represents force or motion. Forefinger represents direction of magnetic field that always pointing to south, and then the center finger represents current. So by using this Fleming left-hand rule, we can determine direction of force or direction of motion. We can look at this example again. This is how Fleming's left-hand rule is applied. Then we can determine direction of force that caused the wire to be pushed upwards. So what is this catapult field? Catapult field actually is resultant magnetic field produced by interaction between magnetic field from the current carrying conductor and magnetic field from permanent magnet. Okay, thus it produces net force on the wire that we call it force on current carrying conductor in magnetic field. Okay, let's look at this example. Let's say there is a current flow through the straight wire. Direction of current is out from the screen. Let's try to look at the pattern of catapult field that produce. The dot here represents direction of current out from the screen. You can see the green color concentric circle is the magnetic field for the straight wire. Direction is anti-clockwise. So you can use right-hand grip rule to determine the direction of magnetic field for the straight wire. And then for the permanent magnet, there is magnetic field directed from north to south. So you can see these blue lines, uniform magnetic field. So what happens next is there will be interaction between magnetic field of the straight wire and magnetic field of permanent magnet. Look at here. Above the wire, direction of magnetic fields are opposite. Thus, resultant magnetic field produced will be weaker. At the bottom part, direction of magnetic fields are the same. Thus, resultant magnetic field will produce stronger magnetic field. So this non-uniform field that produces, we call it catapult field. Due to the non-uniform strength of magnetic field, it will produce net force that acts on the wire. The net force is known as force on current carrying conductor when placed in magnetic field. Direction of the force act on the wire can be determined by using Fleming's left hand rule. What you do, you can adjust your hand so that the forefinger pointing to south, the center finger pointing out from the screen, and then your thumb will pointing upwards. Thus, direction of force is upwards. You can observe when direction of current is reversed, that is current flowing into the screen. Look at the pattern of catapult field that produced for this case. This is a straight wire. Direction of current is into the screen. So we use the symbol cross. Okay, so you can see when the straight wire placed in the magnetic field of permanent magnet, there will be interaction between the magnetic field of both conductor or wire and magnetic field. So it will produce catapult field. Above here is stronger magnetic field, below here weak magnetic field. Thus it produces resultant force downwards that push the wire down. You can apply Fleming's left hand rule to show that direction of force on the wire is downwards. Let's look at activity 4.3. So this is to study factors that affect magnitude of force acting on current carrying conductor in a magnetic field. Apparatus required is direct current power supply, U-shaped steel yoke, 2 pairs of magnet, electric balance, and retort stand. Materials required is copper wire, crocodile clip, and connecting wire. Clamp the copper wire to the retort stand so that it will stay in between the two magnets. When the switch is turned on, you can see or you can observe there is a change in the reading of electronic balance. Let's look at the first situation. If we set the voltage to 1 volt and number of magnet is 1 pair, and then the switch is turned on, initially the reading is 0. When the switch is turned on, we get the reading of the electronic balance is 2.1 gram. Let's increase the voltage to 2 volt. Same number of magnets, 1 pair. The readings become 4.0 gram. And then we decrease the voltage to 1 volt, but now we change the number of magnets to 2 pairs. The reading becomes 3.8 gram. As you can see from here, when there is increase in voltage, there will be increase in reading of electronic balance. Same thing, when there is increase in number of magnets, the reading of electronic balance also increase. So what exactly caused the reading of electronic balance to increase? The wire is placed in the magnetic field of the permanent magnet. When the switch is on, there will be force act on the wire. By using Fleming's left hand rule, the catapult field produced exert a force vertically upwards on the copper wire. But this will cause reaction force to act downwards. That's the reason why the reading of electronic balance increases. The greater the force on the wire produced by catapult field, the greater the reaction force act on the electronic balance. Thus, the reading of electronic balance increases. You watch this video to observe what happens, what exactly happens to the wire and the reading of electronic balance. Let's say the first situation, voltage equals to 1 volt. Initially, the reading of the electronic balance is 0. You observe what happens when the switch is on. So you can see the reading become 2 gram. What caused the reading to increase? Now let's say we increase the voltage to 2 volt. On the switch, you can see the reading now is 3 gram. So we can see from this activity, as voltage increases, the reading of the electronic balance also increases. Okay, look at the second activity. For voltage 1 volt, just now we observed the reading is 2 gram. Now what we do, increase number of magnets to 2 pairs of magnets. Observe what happens to the reading. The reading becomes 3 gram. So from this activity also we can say that when number of magnets increases, the reading of the electronic balance also increases. So the observation from this activity, when voltage increases, the reading of electronic balance increases. This is caused by force that produce increases. Same thing for the second activity. When number of magnet increases, the reading of electronic balance increases because the force produced increases. So from here, what you can deduce from this activity, there are two factors that affect the magnitude of force. The first one is voltage or current. The second one is strength of magnetic field or number of magnets. Let's discuss some questions involving the activity. What is relationship between voltage applied across the copper wire and the current in the wire? When voltage increases, the current in the wire also increases. How does magnitude of current affect magnitude of force acting on current carrying conductor? When magnitude of current increases, the strength of magnetic field around the wire also increases, meaning the interaction between the two magnets will produce stronger resultant force. That's why when the magnitude of current increases, the force increases. What is the effect of strength of magnetic field on the magnitude of force? The stronger the strength of magnetic field, the higher the magnitude of force. Let's look at this activity. We can also carry out this activity to show the magnitude of force and current. The magnitude of force acting on the current carrying conductor in the magnetic field increases when magnitude of current and strength of magnetic field increases. How to measure force that act on the wire? We can measure distance traveled d by conductor. The larger the force produced, the further the distance traveled by the conductor. For this experiment, you can repeat by using different values of current. You can collect 5 sets of data and then can plot a graph for distance traveled d against current. So in this case, distance traveled d represents force that act on the wire. So the same activity that can be carried out is by using the setup of apparatus. So we have this wire hang in this way so that it's able to swing or to deflect. For the first situation, current I1, when the switch is on, you can see the wire swing up or deflect up. You can measure angle of deflection or measure height or swing. Magnitude of force in this case is measured by height of swing or angle of deflection of wire. For the second situation, increase the current to I2. Observe what happens to the wire. You can see the wire swing a bit higher, and the angle of deflection also bigger. The angle of deflection we can determine by using protractor. Let's say for the same current I2, or you can repeat by using larger size of magnet or more numbers of magnet. So when this happens, the force that acts on the wire also increases. As you can see here, the wire will swing up higher than before, and the angle of swing also higher or bigger. Okay? So from here also we can see the factors that affect magnitude of force acting on current carrying conductor, that is current and strength of magnetic field. So that's all my video today. I will continue with the second part for 4.1. Thank you for watching. Bye.